Swayam Prabha. Digital India. Educated India.
Okay, so so we continue with this, this proof of the uh, isoperimetric inequality. Okay, and of course, the isoperimetric inequality, the proof uses this very important Wirtinger's inequality. Okay, and the so what is the Wirtinger's inequality? So you start with a you start with the function capital F, which is defined on close 0 pi, closed interval 0 pi on the real line, and taking real values, and assume that it is C1, that is it's first continuously differentiable. Okay, and assume that it is 0 at the endpoints. Then the Wirtinger's inequality is that the root mean squared value of the function cannot exceed the root mean squared value of its derivative. Okay, and the way we interpret the root mean squared is as square root of the mean of the squares. Okay, but the mean of the squares is to be thought of as mean of, when you take you have to sum the squares, but when you sum the squares over the whole interval, it's this integral of the square function over the integral over the whole interval, and then you have to take the mean, and this will amount to taking the mean value of the integral. So you have to divide by the size of the interval. In this case, the measure of the interval is length, it's pi. So this is the mean of the squares, and then you have to take square root of that. Okay, and similarly you have a similar expression on the right side for the the derivative. Okay, and of course so here capital F dash of t is just d capital F by dt. Okay, this is the derivative, and this is the Wirtinger inequality, and the big deal is that the equality occurs if and only if the function capital F is a constant multiple of the sine function. Okay, so that is the statement. Okay, and somehow if you clear the square roots here in these two, and then you also clear this 1 by pi out, then you get the Wirtinger inequality in this form. Okay, which is that the integral of f squared is never exceeds the integral of its derivative squared. Okay, and it's strictly the equality happens only when the function is a constant multiple of the sine function. Okay, so this is see the philosophy behind these kind of inequalities is that, see, these are all if you take the extreme case of the inequality, it's an equality, and that equality is an Integro-differential equation. Okay, so when I put equality here, what I am getting is integral of f squared is equal to integral of f dash squared. Okay, and you see, if you think, because it involves f dash, this is a differential equation, and because there is also an integral involved, it's what is called an Integro-differential equation. So you are trying to solve for a function f with the property that the integral of f squared is equal to the integral of f dash squared. So you are trying to solve an Integro-differential equation, and the point is that the philosophy is that whenever you find a solution, okay, so any f that satisfies this will be a solution of this differential equation, and the philosophy is that whenever you find a solution, the solution will not only satisfy this integro-differential equation, it will also satisfy the inequation. Okay, so this will always hold in general. Okay, for any function f. All right. So the idea is that somehow the extreme the solution to the extreme case, which is a equation, that solution will also satisfy the inequation. That is the philosophy. Okay, and therefore you see the importance is that you are looking at what happens in the extreme case, which is the equality. And a standard example is the sine function. Okay, because for the sine function, if you compute both integrals, you see that they are equal. All right, and therefore the sine function is one such solution. Okay, but you see this is essentially a first order differential equation. If you think of it as a differential equation, it only involves the first derivative. Okay, and but you see there are boundary conditions. The function has to vanish at 0, the function has to vanish at pi. Okay, therefore the only variation you can get is a constant times the function. Okay, so you get only one constant here. That's the only degree of freedom that you get. Okay, so what is important is to look at you see the extreme case. Okay, and the extreme case is the case when f is equal to d sine t, but that is when you get equality. That's what the result says. But that means that when you have equality, the solution of this integro-differential equation is, if you take f of t by sine t, it is a constant d. So that tells you that you have to look at this function g, which is f of t by sine t, and you see at 0, of course you are dividing by sine t, therefore there's a problem at 0 and pi. But because f at 0 and pi are also 0, because of L'Hopital's rule, this g is also defined at 0 and pi, and it's a good C1 function. Okay, and therefore the trick is that wherever f comes, you have to use this g. So finally we were able to show that the inequality holds, and the equality happens if and only if the g is a constant, and which is equivalent, of course, g is of course f of t by sine t, and that is equal to d. So f of t equal to d sine t is the case when you get the equality. Okay, so this is the Wirtinger inequality. Now what we need to do is that we have to put this to use to prove the isoperimetric inequality. All right, now so we start with the following thing. So proof of the isoperimetric inequality. So what we do is that we have to take so what is a isoperimetric inequality? You have to take a closed curve. It has to be simple, and it has to be smooth and regular. Okay, and then the perimeter, that is the total arc length of the curve, that is kind of fixed, and you allow the curve to vary, and then you want to say that the area enclosed by the curve is maximum only when the curve is a circle. Okay, that's if and only if. So if you take a general curve which is not a circle, then the area is lesser than the area of the corresponding circle for which that perimeter is already given. Okay, so suppose so we start with gamma, a simple regular closed curve. Okay, so with length or perimeter, or if you want arc length, L of gamma, which is some L naught. Okay, so this the point is the the length of the perimeter is fixed, okay, and enclosing an area A of gamma. Okay, so the picture is like this. You have, so you have this. So gamma is a curve like this. So I have some starting. So I can fix a starting point and ending point, and I have this. This is the curve gamma, and so if I measure the arc length all the way across along this arc, that is L of gamma, okay, and this is L naught, and whatever is inside the area enclosed, this is going to be A naught. I mean, so it is A of gamma, okay. So it's A of gamma, all right. Now, so there are a few things already at work here. You see, to make sense of the area enclosed by a curve, okay, you already need you need the Jordan curve theorem, okay. So and the most important thing in the Jordan curve theorem is that you see it's a simple closed curve, okay. Mind you, for the Jordan curve theorem you don't need regular and smooth and all that. The Jordan curve theorem is a kind of continuous curve theorem, okay. The only condition on the curve is it is simple. That means it doesn't have any self intersections, okay. And but the important thing is this area enclosed by the curve, that to make sense of that, I need to understand that there is a region of the plane that is enclosed by the curve, and that is guaranteed by the Jordan curve theorem, okay. So that is very, very important theoretically, because if you take an abstract curve, okay, whose shape you do not know, you still need to know that it really encloses a bounded area, okay, a well defined area. Now that is guaranteed by the Jordan curve theorem, okay. So to make sense of this A of gamma, you need the Jordan curve theorem, okay. And for the Jordan curve theorem you need simple closed curve. Mind you, smoothness is not required, just continuity is enough, okay. So it's a deep theorem, all right, but we are using it in that sense. Now you see, of course, to deal with this kind of curve, you can usually take any parametrization, all right, and the easiest parametrization is always arc length parametrization. So what you do is that you take arc length parametrization. The arc length parametrization will be for S, the arc length varying from 0 to L of gamma, which is L naught, okay. And so what is this L naught? This is just L of gamma is just integral from 0 to L of gamma itself of ds, okay. So this is your arc length, all right. ds is the element of arc length, all right. And what is the isoperimetric inequality statement? The isoperimetric inequality statement is that the area of this curve is maximum only when the curve is a circle, okay, with the same perimeter, okay. So A gamma is less than or equal to area of a circle with a perimeter L naught is equal to L of gamma. And what is that? So you see, if you take a circle like that, then and it has a, say, radius r naught, all right, then the perimeter is going to be it's going to be 2 pi r naught, and this has to be equal to L naught, okay. Therefore your r naught is going to be L naught by 2 pi, and therefore this area is going to be just L naught squared by 4 pi squared, okay. And so I have to write, so the area should be pi r squared, so I have to write pi. So let me write this, it has to be equal to pi into r naught squared, so that is pi into this, all right. And so I will get L naught squared by 4 pi, okay. and mind you, this L naught is just L of gamma, so it's L of gamma squared by 4 pi. So basically, you are getting this inequality. A of gamma is less than or equal to L gamma squared by 4 pi. So this is the inequality. And the important statement is that equality will happen if and only if the curve is a circle, okay? With equality if and only if gamma is a circle, okay? Now, so this is what you have to prove, all right? So you see, so the trick is we have to use the Wirtinger inequality, okay? And what is this Wirtinger inequality about? See, it is about a function which vanishes at 0 and pi. It's a function defined on 0 to pi, just like the sine function or any constant multiple of the sine function. It vanishes at 0 and pi, okay? And it's a C1 function, all right? And then the Wirtinger inequality is that the integral of f squared, integral of the square of the function, does not exceed the integral of the square of the derivative of the function, okay? Equivalently, the Rm, the root mean squared value of the function, does not exceed the root mean squared value of the derivative, okay? So it is the way we have stated our Wirtinger inequality. It's valid for functions from 0 to pi, with functions vanishing at 0 and pi. And what we have is we want to apply it to this curve, okay? And this curve, you see, you have this parametrization gamma of s, let us say. Then this gamma of s is going to be defined on 0 to L of gamma, okay? And one would like to therefore scale it to 0 to pi, okay? So you introduce a new variable, obvious variable. So you see your arc length, it goes from 0 to L naught, okay, which is of course L of gamma, let us say. And then you want to scale it to 0 to pi, so what you do is you divide by L naught. So this becomes 0 to 1, okay? And then multiply by pi, so you'll get 0 less than or equal to s pi by L naught less than or equal to pi. And you call this variable as t. So this is your new variable t, okay? So if you take gamma of t, okay, which is equal to small gamma of s, okay, if you put it like this, okay, then basically it is just a reparametrization of the curve, all right? So this gamma of t will be so this is just capital gamma of s pi by L naught, and this is equal to small gamma of s, okay? So you see this gamma will be from 0 to pi into R2, and it's a reparametrization of small gamma, which is arc length parametrization. It's going to go from 0 to L naught into R2, okay? And why is this a regular reparametrization? Because in this case, what you notice is that you see it's because of this thing. You have this very nice thing that if you calculate ds by dt, ds by dt is just it's going to be what? It's going to be, so you see s is t L naught by pi, okay? Therefore ds by dt is L naught by pi, okay? And this is of course a constant. And so mind you, L naught and pi are both not 0. Therefore ds by dt is a constant and it's never 0. So it's a regular parametrization, all right? Now this this silly thing that ds by dt is L naught by pi, and mind you, that is also equal to L of gamma by pi, okay? Because L naught is L of gamma, all right? Now it's a silly observation, but it is very, very useful, okay? And we are going to use it in a very tricky way, as we are going to see, okay? So so this reason for moving from arc length parametrization to this new parametrization is just to get the interval from 0 to pi. Okay, I want to apply the Wirtinger's inequality. Now, what we do is that we want to prove this inequality, and we have to show that the equality is obtained only when gamma is a circle. Okay, otherwise it's a strict inequality. All right. So how are you going to do this? So you see the LHS is what? The LHS is area of gamma. Okay, all right. This is the same as area enclosed by capital gamma. Okay, mind you. So let me write this carefully. This is area of gamma of S, and this is area of gamma of capital gamma of T. Okay, so so you see you have a closed curve. Now I am going to think of only this small t as a parameter, and small t is varying from 0 to pi. 0 is the starting point, pi is the ending point, and they are the same because it's a closed curve. And I am going to assume that this starting and ending point are the origin, okay? Because I would like to apply Wirtinger's inequality, that you need a function which at the endpoints of the interval vanishes, okay? So so what I'm going to do, the function for which I'm going to apply, it's not the function for which I'm going to apply the Wirtinger's inequality. Mind you, it's a real valued function, whereas gamma is it's a vector valued function. Gamma is R2 value. Okay, so what you're going to do is you're going to apply it to the the distance of the point gamma from the origin, that function. So that is the R coordinate in the polar coordinates. Okay, so that you get a real valued function. So what we are going to do is that you are going to write this gamma of t, which is going to be x of t comma y of t. You are going to write it in polar coordinates. You are also going to write it as r of t and theta of t. You are going to write it in polar coordinates. Okay, and I would like, the point is that I want to, of course t is going to vary from 0 to pi. Okay, therefore this r in both I mean in all the four, in fact x of t, y t, r t and theta of t, t is of course going to be varying from 0 to pi, and I need to have a function, a real valued function on 0 to pi, which vanishes at the endpoints, to apply the Wirtinger. Okay, and what I am going to do is I am going to choose this r of t. See, this r of t is actually distance from the origin. Okay, and I am going to put r of 0 equal to 0 and r of pi equal to 0. That means that the curve starts at the origin and ends at the origin. Okay, so that is an assumption I am going to make, and this is always possible because I can always translate the initial point of the curve to the origin and look at the new curve. Okay, and when you translate the curve by a translation, you see its arc length, the area that it encloses, etc., they don't change. So without loss of generality, I'm going to make that assumption. So we will assume, of course, without loss of generality, that r of 0 is equal to r of pi. Okay, that is the curve capital gamma starts and ends at the origin. Okay, so we assume that. All right, so the picture is somewhat like this. You have a curve starting at the origin. Okay, and it goes all the way and it comes back. It's a simple closed curve, and then there is this area enclosed by the curve. So let me use capital gamma. Okay, and which capital gamma is the same as small gamma. Okay, except for a parametrization, and this is the arc length is L naught, which is L of capital gamma. Okay, mind you, of course, arc length, area, etc., they are all independent of the parametrization, right? So this is my curve. Okay, And now what is it that I am trying to prove? This is the inequality I am trying to prove. A gamma is less than or equal to L gamma squared by 4 pi. We want to show A gamma is less than or equal to L gamma squared by 4 pi. This is what you want to do. Okay. Now, how do you relate A gamma to the curve? Mind you, A gamma is the same as A capital gamma. Okay. And this is the same as L of capital gamma squared by 4 pi, and this is of course L naught squared by 4 pi. Okay. And I have put that L naught because the idea is that you want to think of various gammas for which the arc length is the same L naught, and then you are trying to look at the various areas, and you are trying to say that all these areas are bounded by this L naught squared by 4 pi, which is the area of the circle case, for the circle being the curve with the same perimeter L naught. Okay. Now, we want to show this. How do you calculate area? Area can be calculated in polar coordinates. So it's the area element is is r dr d theta. Okay. If you write it in two variables, and in one variable it is this r dr, if you think of r as a function of theta, okay, then you integrate r and have only theta limits. Okay. Then this is also half r squared d theta. Okay. And you can also write it as so this version is used when you have both r and theta limits. But if you can write r as a function of theta, this is the version that is used for theta limits. Okay. And half r squared d theta is also written as half r squared theta dot dt, where theta dot is d theta by dt. Okay. So this theta dot is just d theta by dt, and I have to bring it to t because t is now the parameter with which I am working. Okay. So this area of gamma will be integral from 0 to pi half r square theta dot dt. This is what is the left side. Okay. So that is, you want to show that this is the left side. On the right side you have L gamma squared by 4 pi. Okay. Now you see this L gamma squared by 4 pi also, the idea is I want to use the Wirtinger's inequality. The Wirtinger's inequality is that first of all it is you are saying that integral of function squared cannot exceed the integral of the derivative of the function squared. So it's an inequality on both sides. You have integrals, and what I have managed to have is on this side I have an integral. I have to bring an integral on this side. Okay. Now the most obvious thing that you would try to do is that this L gamma squared is actually L gamma the whole squared. This is writing it in terms of a small s, which means I use small gamma. If you want to write it in terms of small t, which is, then you have to use capital gamma. So this is going to be L of, also it's also going to be L of capital gamma. Okay. And whole squared. And if you want to write it like that, it's going to be 0 to L of course capital gamma. And here for if you use capital gamma, then you have to integrate the speed. Okay. So you have to integrate gamma dot. You have to take gamma dot. Okay. And you have to take norm of that, and then you have to put dt. Okay. And mind you, so what this will give you is gamma. See, gamma of t is simply that is something that we have already written here. Gamma of t is just small gamma of s, of course. So there is really no big deal. All right. And it's it is capital gamma of s pi by L naught. So if you write it like that, it's small gamma of s. So of course it will be the same thing. Okay. And of course I will get a square here. See, the problem is that on the right side, left side I have an integral. Okay. Right side I seem to be getting square of an integral. Okay. And the point is that somehow you have to make it just an integral. I should have an integral on both sides. Only then I can apply the Wirtinger. So there's a rather sneaky trick. Okay. It's kind of but it's very silly. So the trick is that to avoid this square here in the integral, So what you do is, you take the RHS, the right hand side is L gamma squared by 4 pi. So what you do is that you write it as L gamma, all right, and by 4 pi, and then you see this so incidentally, let me also say something else before that. So you also have, so here is the important thing. See, you also have that this S is T, so you see this S is T L naught by pi. So ds by dt is actually L gamma by pi. Okay, so we have this thing here. So S is so this S is T times L naught by pi. So ds by dt is therefore it's L naught by pi, so which is L gamma by pi. Okay, and therefore this L gamma by pi can be, so this L gamma can be written as pi ds by dt. Okay, that is also something that you can make use of. So if you do that, what you will see that this right side term, this L gamma by pi, okay, it will convert that L gamma by pi into a derivative. Okay, it will convert the L gamma by pi into a derivative. All right, and so you have to use that cleverly. Note also, so let me write this here. Note also, you see that S is equal to, so let me write that again here, T L naught by pi, T L naught by pi, which is T L gamma, T times L of gamma by pi, and then ds by dt is therefore L gamma by pi. And if you therefore you see this L gamma, this right side can be completely made into a derivative. So you can actually write the right side also as, so if you do it like that, then what will you get? You will get, you see this L gamma is pi, so let me write it here. So what I will get is pi ds by dt, the whole squared by 4 pi. Okay, and so what I will get is, pi by 4 ds by dt the whole squared. Okay, this is also true, but this is also useless, because the point is I don't want, I'm getting square of a derivative. Okay, and if I write it like this, I'm getting square of an integral. So there is a small but a silly manipulation that has to be done, and the silly manipulation is that, the right hand side will be, so you write it as L gamma squared by 4 pi, and then what you do is that so you keep one L gamma by 4 pi out, and then write the other L gamma as integral 0 to s ds, so 0 to L gamma ds. Okay, because if you integrate this, you will get L gamma. Then what you do is that you write it as L gamma by 4 pi, and then you write this as 0 to L gamma, this ds, you write it as ds by dt, and then once you put this dt, you change the limits to t equal to 0 to pi. Okay, so this will become 0 to pi. Okay, and then use the fact that this ds by dt is, there is, you see, this ds by dt is also L gamma by pi. So what you do is that, you push, so here is the clever thing to do. What you do is you push this, you push 1 by 4, okay, you push this L gamma by pi inside. So it will become integral 0 to pi L gamma by pi into ds by dt into dt. Okay, I am able to push it inside because this is a constant. Okay, and then change it into the derivative. Okay, so it's completely, tricky. So then you write it as 1 by 4 integral 0 to pi, and this L gamma by pi, mind you, is ds by dt. So you get a ds by dt the whole squared dt. Okay, so it's rather curious. Okay, it's kind of very sneaky. All right, and I mean, all this is happening because this ds by dt is a constant. All right, but the trick is that I am able to get an integral on the right, which is what I want. Okay, so essentially, so we have to prove. So we have to prove. You see, on the left side, I have this fellow, half 0 to pi integral half r square theta dot dt. okay, less than or equal to, on the right side I have this guy, 1 by 4 integral 0 to pi, ds by dt the whole square dt. This is what I have to prove. So now I have one integral less than or equal to another integral. So this at least looks like the case where I can apply Wirtinger. Okay. Now, but the point is that here everything is in r and theta. There is still this ds here. The s is still sticking around. I have to change that to r theta. Okay. So that is a very easy thing, because you see, ds squared is dx squared plus dy squared. Okay, element of arc length. So ds by dt the whole squared is nothing but dx by dt the whole squared plus dy by dt the whole squared, and x is so x is r cos theta. Okay, to write it more carefully, and of course y is r sin theta for polar coordinates, and to write it more carefully, x of t is r of t cos theta of t, and y of t is r of t sine of theta of t. Okay, and therefore you calculate, you change everything into r and theta. Okay, so you see dx by dt, if you use the chain rule, you differentiate x of t is equal to rt cos theta t. Using the chain rule, you will get, you keep rt constant, r constant. Cos theta, when you differentiate, you will get minus sine theta, and then you will get a theta dot d theta by dt. Okay, plus you keep cos theta t constant, and you differentiate r, you will get r dot cos theta t. Okay, similarly, if you do dy by dt, what will happen is that you have to differentiate r sin theta. So you keep r constant, you differentiate sin theta, you will get cos theta, and you will get a theta dot. Mind you, you are differentiating with respect to t, plus the other term will be r dot into sin theta. Okay, and now I need this expression. I have to square and add these two guys. Okay, so if you square and add these two guys, what will you end up with? So you see, this r dot squared cos squared theta plus r dot squared sin squared theta is going to give you an r dot squared, r squared theta dot squared into sin squared theta plus r squared theta dot squared into cos squared theta. Okay, so essentially what you will get is, if you square and add, ds by dt the whole squared will become, these two terms will give me an r dot squared. Then these two terms, sum of squares is going to give me an r squared theta dot squared. Okay, and then the mixed terms will cancel out because there is a difference in sign. Okay, so the first term, when I square, I will get a 2r dot theta dot sin theta into minus sin theta cos theta, and I will get the negative of that here, that will go away. So the nice thing is that this is what it is. So this fellow on the right side is nothing but r dot squared plus r squared theta dot squared. Okay, that is what it is. Okay, so now we are in a very good situation. So we have to prove, thus we have to prove on the left side you have integral 0 to pi half r squared theta dot dt is less than or equal to, and on the right side you have 1 by 4 integral 0 to pi, and this term here is r dot squared plus r squared theta dot squared dt. This is what I want. This is what I have. Okay, so I have to prove this. So what you do is you bring everything to one side. All right, so that is, you want to show 0 less than or equal to, I'll put let me take everything to one side and take a half outside. So I'll get 0 to pi. So I have this term r dot squared plus r squared theta dot squared, and then from this side I'll get a minus 2r squared theta dot into dt. Okay, this is what I have to prove. All right, is that right? Sorry, I think I should put a 1 by 4 here, right? That's right. Yeah. So so proving this is equal to proving this. All right, I bring this term to the right side. Okay, and then now you see, there is a, if you look at these two terms, there is an r squared which you can pull out, and what you get is theta dot squared minus 2 theta dot. That can be, the square of that can be completed as theta dot minus 1 the whole squared. Okay, so you see this term here is r squared into theta dot squared minus 2 theta dot, and this is equal to r squared into theta dot squared minus 2 theta dot plus 1 minus r squared. Okay, complete the square so that this becomes r squared into theta dot squared theta dot minus 1 the whole squared, right, minus r squared. Okay, so therefore the net effect is that need to prove, so I keep writing to prove 0 less than or equal to 1 by 4 integral 0 to pi. So I'll get so I get this r dot squared plus I have to write this term. So I will bring this minus r squared here. Okay, that's one term, and then this r square times theta dot minus 1 whole square, I'll write it as another integral. So it's 1 by 4 integral 0 to pi, r squared into theta dot minus 1 the whole squared, and of course there's a dt everywhere. Okay, this is what I have to prove, right? And I don't have to worry about this term because it's a square. The integrand is a square, it's non-negative, and then I'm integrating it, so it's non-negative. So I have to only worry about this term, and this is exactly the derivative squared minus the original function squared, and that is the integral of that is always greater than or equal to 0 by Wirtinger. So here is where the Wirtinger is applied. It's applied to the function r, which is the distance from the origin to the curve, assuming the origin is the starting and ending point of the curve. Okay, so at the starting point r is 0, the ending point r is 0, and cleverly the parametrization has been done on 0 pi. Okay, so the moral of the story is, by Wirtinger inequality, okay, this term is always greater than or equal to 0 with equality. The equality happens only when the function is constant multiple of the sine function. So with equality, if and only if you see r of t is d sine t, d a constant. Okay, so but if you want everything to be 0, then this should also become 0. Okay, so of course this term is always I should say this term is always greater than or equal to 0. Okay, and if it is 0, it's the integral of a non-negative function is 0, then the integrand has to be identically 0. So it means r squared into theta dot minus 1 the whole squared is 0. But you see r squared is certainly not 0. Okay, so it means theta dot minus 1 has to vanish. Okay, so the RHS vanishes if and only if also so I should say if and only if, not only that is both should happen. I mean, it's a sum of two terms, both of them are non-negative, and if you want that sum to be 0, each term should vanish. Okay, the first term vanishes only if r of t is d sine t by Wirtinger. The second term will vanish if and only if theta dot equal to 1. Okay, so if and only if r of t is equal to d sine t and theta dot is equal to 1. Okay, so both should happen. But you see, d theta dot is d theta by dt. This is 1. So this means theta equal to t plus alpha. Okay, therefore you put these two together, you get equality happens if and only if you have this r of so let me replace everything by theta. So so t will be theta minus alpha, so I'll write it as r of theta minus alpha r of theta minus alpha is equal to d sine theta minus alpha. So I think it's better to keep this as t itself. r of t is d of sine theta minus alpha, and you know your the and t is of course from 0 to pi, and geometrically this is a circle. Okay, so to see that there is a very simple diagram. So what you do is that you take you take this angle alpha, okay, and so there is this line. Then what you do is that you draw this circle with this as tangent, and you take the diameter to be d, right? And then if you take so if you take some point given by r of t, okay, which is given by this angle which is going to be theta of t, okay, then you see that if you join this whole angle is theta, okay, and this is alpha, so this angle is theta minus alpha, okay, and therefore this is also theta minus alpha, and this is d, okay, and if you this angle is also 90, okay, and therefore you see this distance, okay, is going to be d sine theta minus alpha. Because it's side opposite to this right triangle. The side in the right triangle, it is the side opposite to the angle theta minus alpha, and the hypotenuse is d, is the diameter. Okay, so this r of t is going to be d sine theta minus alpha, and you see therefore as so it is a circle. So which is a circle. So the so therefore you see the equality occurs only when the curve is a circle. Okay, so it's a clever manipulation of these things, but it's very simple calculus, except for the only deep thing is the Wirtinger inequality, and the Wirtinger inequality is kind of is very it's a very general philosophical kind of inequality, and it is what is the manifestation of the isoperimetric inequality in great generality. So even in something as broad as what is called a Sobolev space, you have these kind of isoperimetric inequalities, and they are called Sobolev inequalities. Okay, so this is a very general thing, but for that you see this is a pretty easy thing to prove. All right, now yeah, so there is a so that finishes the proof of the for the isoperimetric inequality. The thing that one has to worry about is so here is a question that you have to ponder about. Where have we used the fact that the curve is simple? Okay, so of course, as I have already told you, we have used the curve to be simple, to be able to define the area enclosed by the curve, the region enclosed by the curve, and that is guaranteed by the Jordan curve theorem. So that is one important thing. There is one more place where the simplicity of the curve has been used implicitly, and that is here. When we wrote this, when we wrote the area, like this, where is this? See, when we wrote the area as half r squared theta dot dt, okay, there is the simplicity has been used, okay, and the reason is, you see, what you must understand is that if this theta dot, remember that if theta dot is negative, that is if theta is decreasing, okay, one should not confuse theta with t. See, t is the parameter, it's varying from 0 to pi, so it looks like an angle, all right, but it is not the polar angle. The polar angle is theta of t. The polar angle is theta, and theta depends on t, okay, and t is only a parameter. though it is from 0 to pi. The real angle in the picture is actually theta. So as t varies from 0 to pi, as the curve moves, you see this theta will also change. And theta can have local maxima and minima. Theta can increase and decrease in subintervals. So this theta dot can change sign, right? Therefore, you see this, when you write this theta dot, this can have a change of sign. The other term half r squared, that will not create any problem. Okay, so integrating this as it is and saying that it will give the area, that is where the issue is. That's where you will need that the curve is simple. Okay, if the curve is not simple, what will happen is that if you blindly integrate this, wherever there are portions of the curve between self intersections, areas will get subtracted. This is just like, if you integrate a non-positive function, real valued function. I should not say non-positive. If you take a real valued function which can be either positive or negative, if you blindly integrate it over an interval, you will not get area under the curve. What you will get is, you will get the area above the x-axis minus the area below the x-axis. Okay, if you want really the area under the curve, you have to integrate mod f, the modulus of the function. Okay, otherwise what will happen is, whenever the curve goes below the x-axis, that portion of the area will come out to be negative and it will get subtracted. Okay, and that is the same kind of thing that can happen to this integral if theta dot, if you blindly integrate half r square theta dot. But the interesting thing is, even for a simple closed curve, this theta dot can change sign. Okay, it can change sign and it will. But the point is, in spite of that, you see, if you integrate this, you will exactly get the area under the curve, the area enclosed by the curve. That is the whole important thing. Okay, and the simplicity is used there. Unless you have a simple curve, this left side will not give the correct area. That's another point where the simplicity of the curve is used. Okay, for EF gamma. Yeah, so usually the way this is done is that, so for example, if you look at the area formula, the way we usually do it is, you see, you take in the in the polar sense, what you do is you take theta equal to theta 1 and you take another rate theta equal to theta 2. Okay, and then what you do is you take a curve which is given by r is equal to f of theta. Okay, then this area here is given by integral from theta equal to theta 1 to theta equal to theta 2 of half r square d theta. This is what you do. Okay, now what is going to happen in our case is that, when you do it over successive pieces of the curve, then the orientations will get reversed. Okay, and when you subtract, you will get what is in between those pieces, and that's how it works in this case. And it is also important that the curve is oriented in such a way that as you travel along the curve, the area that is enclosed should lie to its left. So there is a positive orientation. That is very, very important. Okay, we also need that. Okay, so for example, you can think of a pretty complicated curve like this. I can think of a curve like this. So I want a curve that leaves here and it comes back here. But what I could have done is, I could have done something like, if you think about it, I could have, so what is the easiest example I can think of? Yeah, I can keep going around like a spiral, essentially. So you see, I can do something like this. See, you go like this. Okay, see, it can be like this. See, my simple closed curve can be like this. okay, and yeah, so just let me complete for a moment. So you see, you can have a curve like this, okay, and then you see what will happen is that you see the area, the region enclosed by the curve is still well defined by the Jordan curve theorem, okay. Mind you, this is still a kind of quite an easy curve in the sense that I can draw it and I can figure it out, but you can imagine that if it is a very general curve, you can't even picture something like this, okay. But the point is that if you take any theta equal to theta 1 and theta equal to theta 2, then you see what will happen is that when you are integrating on this portion, okay, you will get this area, and here you see you are going like this, and then what you do is that when you come to this segment of the curve, so you look at the other segment of the curve, which is this segment of the curve, you see you are now going the opposite direction, and the area will be this whole orange thing. And because of the opposite direction, you see the signs are different, so they will get subtracted. So essentially what will happen is that the area in between is what is going to get reflected, okay. And this will happen everywhere, it will happen everywhere. You will pick up the area here, you will pick up the area here, okay. And that is how you actually end up getting the the area inside the enclosed by the curve. And here you see you see what is going to happen. Actually I have oriented this curve in the wrong way, because you see I have given the way I have drawn it, the area lies to the right of the curve. And the problem with this kind of orientation is that you see the smaller area is positive, okay. This area, you see this area, this is positive because the curve, this is in the the curve is moving, the area is to the left of the curve. Whereas if I take this whole area, which is all of this, that is negative. That is because now the curve is it lies to the right of the curve. When I add both, what I will get is I will get negative of this, okay. So what you will do is that if you integrate half r square theta dot on this, what you will get is a negative of the area enclosed, okay. That's because of my wrong orientation, okay. Why is this orientation wrong? Because the enclosed area lies to the right of the curve if I walk along the curve with that given orientation, okay. I have actually given the clockwise orientation, which is the negative orientation, okay. So so that is so simplicity is used, okay. No, you see, take this argument. You take, for example, if I understand what you are trying to say. What you are trying to say is that this half r square d theta works only when r is a function of theta, and you are saying that for a given value of theta, that means you should get only one r, but for a given value of theta, you are getting several r. That is your problem. Yes. So the point is that you see here what is happening is, so this is the in some sense, by changing by not integrating over theta, but by integrating over t, which is a parameter for theta, you are actually avoiding that. Yeah. So the proof is the following. The proof is literally that the integral from, let us say, theta equal to theta 1 to theta equal to theta 2 is by this geometric argument. No, you're right. No, he is right. See, see, the point is, I am not getting into how the how the Riemann integral is defined and how the area integral is defined and all that. I'm just saying, I mean, if you look at it from a very naive point of view, normally to get the area, what you will do is you will integrate from theta equal to theta 1 to theta equal to theta 2 half r squared d theta. That's what you will integrate. But now theta being a function of t, you have to integrate between t limits, and it will be rt squared. The d theta will become d theta by dt dt. Okay, so you will get r squared theta dot dt. But the point is that this kind of issue, that now no longer is r a function of theta, okay, but the point is that both r and theta become functions of t, and in that case that the formula still works requires a proof, and that proof is exactly this. So I am saying that, and to make this kind of a proof, you need to be able to identify the what is inside the curve, and that's exactly where the simplicity is used. See, had you taken a curve like this, let us say, suppose I started like, so if I started like this from this point, and suppose I say I went like this, think of something like this. Okay, now you see, for this kind of a curve, okay, if you look at it, then you see this area is positive. This is positive orientation, whereas so this is positive area, and then whereas if you take this region, it is clockwise, so this is negative area. Now, so this is a curve which is not simple. If you integrate r square half r square theta dot for this, you will actually get this minus this. You will not get the full area. So this that it should not have self intersections is a big issue. I mean, you cannot have self intersections if you want the areas to add up properly. So the simplicity is important. On the other hand, of course, it is correct to say that the formula theta equal to theta 1 to theta equal to theta 2 half r squared d theta is in general valid only for r equal to f, a function of theta. But when you consider a situation like this, for a given value of theta, there are several values of r. So as it is, it cannot be directly applied, but you can make a geometric argument like this and say that if you change theta and r both to a function of a t, and you do integration over t, if the curve is simple, then it is still fine. Okay, so then r need not be a function of theta. Both are now functions of some t, and then it works. Okay, so that's important. So simplicity is very, very important. Okay, so I think so that finishes the isoperimetric inequality. What we need to next look at is a 4 vertex theorem. Okay, that's the next major theorem, right? We'll do that next.